Hey there, calc folks, back here with what I hope is another quick video in our application of integration and vector valued functions, right? Like I said, we've been looking at vector valued functions. We introduced the calculus of vector valued functions, derivatives, limits, derivatives, integrals, right? And now we've been looking at a little bit of application. I think we've looked at the unit tangent vector. And in this set of notes, we look at net change and future value of vector valued functions, which is an application of integration. The unit tangent vector was an application of differentiation. So that is what we want to get into today, is look at that application of integration with vector valued functions, and we can look at it in this context of what we know as net change, right? And then use net change to go just a little further with that calculation and develop what we call future value calculation. So let's take a look at the set of notes. Here's our notes. Right? To begin with, net change and future value of vector valued functions is what we're looking at here. And recall, net change and future value were concepts presented back in Calculus 2. Right at the beginning of that semester back in our Calc 2 sequence, or back in a Calc 2 class somewhere, you're typically presented with the concept of net change. Usually you come back to Calc 2 with looking at some application of the integration process, and this is one place that integration is used. The integral calculation can be used to figure out how much a quantity changes in its net change over some interval of the independent variable. All right, and that's known as net change back in calculus, right? If we look at the net change in some quantity q of t we were presented with, over some interval t in this closed interval from a to b, that net change is the overall change in the quantity over that interval of the variable t, right? That is q of b minus q of a in value, where we learned back in the calculus that if we are not given the quantities function null description with respect to the variable t, but if we have q prime of t, the rate of change in the variable with respect to our variable or our parameter t, that we are able to calculate the net change. We are able to calculate that net change using that rate of change in our quantity, and that would be what involves the integration process. We can integrate from a to b the value of q prime of t dt, and we can gain information about how q changes on this interval of the parameter t from a to b. All right? So that is what we want to recall, and we're going to see this come back in the context of vector valued functions. All right? Similarly, within the context of vector valued functions, we might see net change presented as follows, right? For a vector valued function given by r bar of t, right? In n-dimensional space, given the rate of change in a vector valued function r bar, that would be the quantity r bar prime of t. The net change in r bar over values of t in this interval from a to b, right, is given by the following calculation. And you notice it looks very similar to what we have above, except it incorporates the use of vector valued functions as opposed to that scalar value quantity described by the function q of t given above. All right? Net change for vector valued functions is a change in a vector valued function over values of its parameter t in some closed interval from a to b. It is the difference between the value of the vector valued function at the latter value of t minus the vector valued function's value at the earlier or previous value, I should say the earliest value of t on that interval from a to b. All right? And if we do not have our vector valued function r bar of t, But we have the rate of change in our vector valued function, r bar prime of t. We can actually integrate over that interval from a to b, r bar prime of t, and develop the calculation for this net change quantity. Right? Let's look at a quick example. Again here, when calculating net change using integration, typically not going to be given r bar prime of t, r bar of t, you will be given r bar prime of t. Right? Here we might be told the rate of change in our vector valued function, r bar prime of t, is equal to the two-dimensional vector t comma e to the t. And we want the net change in r bar over values of t in that simple interval from 0 to 1. Well, what the above formula does tell us is that net change in our vector valued function r bar of t, right, over this interval from 0 to 1, given r bar prime of t, is this calculation here by definition, right? Where if we apply our integration process to the integrand t comma e to the t, the antiderivative of t is 1/2 t squared. The antiderivative of e to the t is e to the t, and we're going to evaluate this across those bounds from 0 to 1, which means we're going to take its value at 1, which would be 1/2 comma e, and subtract from it its value at the lower bound of 0. That would be the vector 0 comma 1. So vector 1/2 comma e minus the vector 0 comma 1 is the vector 1/2 comma e minus 1. Right? And that vector describes the net change in the vector valued function r bar of t. Right? That net change is a vector description that has both a magnitude and a direction. And one thing we might note here is, let's go back in the definition and maybe say this, because I didn't put this in the notes. The direction of the net change vector indicates the direction of this change, whereas the magnitude of this vector, right, indicates, right, the displacement of this change, right? How much does it displace by in terms of distance, right? Or, how much does it displace by in terms of distance, right? So it indicates the displacement of this change in the indicated direction. All right? We'll say it that way. Remember your... we'll leave it at that. That is how we interpret net change, folks. So in this example, folks, as we see here, our result is a vector. That vector has a direction to it. It does indicate the direction of displacement from our starting position at r bar of 0 to our ending position at r bar of 1. And the total distance between those two locations would be given by the magnitude of this vector. Right? Now, folks, in order to actually, however, visualize what that net change would be highlighting from r bar of 0 to r bar of 1 to describe this overall change in displacement, right, throughout that space, including the direction, this net change, you would have to know where you would be positioned at r bar of A. Right? You could certainly take your position at r bar of A, add to it this displacement vector, right, this net change description, and it would point to the value r bar of b. You could get that by adding r bar of a to your net change. Adding r bar of a to both sides of this relationship would give you r bar of a plus net change would be equal to your location at r bar of b. Right? So this is the ways to start to think about how net change would be interpreted. But what it also allows us to do is we can not only can add that r bar of a to net change to come up with this interpretation, we can take r bar of a, add it to the right hand side of this definition, right, and obtain information about r bar of b using the integration calculation. Now, what this allows me to do is to go on to say is if I just have a little bit of initial position information, if I just have a little bit of information about specific location in space at, say, time t equal to a, I can use that information along with the rate of change in that position in space, r bar prime of t, over some interval of t, starting at a and going up to b, to actually come up with a description of the overall change, or the description of position r bar of t at any point in time t after that observation at t equal to a. I can use this definition for net change to develop a definition for the future value of a vector valued function, or to develop what we sometimes call the future value function. Or I can use it in the context of r bar prime of t. I can use it to develop the description of r bar of t. All right? Where I can describe position with just a quick little observation of position and knowing its rate of change in position. All right? That is future value, folks. So I do break down that development here in the notes, right? As with net change, and this was something we saw similar back in Q at T. We saw this happen back in Calc 1 with just net change in general. The calculation for net change of r bar of t can be manipulated to obtain a calculation for future value of r bar of t. Consider adding r bar of a to both sides of this calculation as I had described previous, right? You would end up with r bar of b equal to r bar of a plus that integral calculation we saw in the formula given above on the right-hand side. Well, if we consider this result for a moment, and consider for just notational purposes letting a equal t is 0, be some specific time of t, right? B equal to t, right? Let b equal to t. B equal to t, right? The parameter in general, we're just going to let b be replaced with t, the parameter in general, and let then t equal u, a dummy variable, right? The result given above is the future value of r bar, right, for values of parameter t greater than or equal to t null, right? That t sub 0 value, that observed value of time, all right? Or position at a observed value of time. Now, a equal to t null is that unit of time, though. Specifically, r bar of a is that specific observation of position at that specific unit of time. All right? We see this given in the definition, right? This transformation given here in the definition. Given r bar prime of t and r sub n, given that rate of change in our vector valued function in n-dimensional space, and given r bar of t null, the observed position at an observed point in time, right? The value of r bar at the specific value of, r bar of t, the value of r bar at that specific value of time. The future value of r bar for values of t greater than or equal to that observed value of time is given by the following. And what you see here is we can develop a vector description of our vector valued function r bar of t by simply taking our observed position along that description at time t null, that observed point in time, and add it to this integration calculation involving the rate of change in our vector value function. All right? Oh. This value seen here, r bar prima u. U is just going to act as a dummy variable, we say. We're just replacing the t seen above in that equation with u to be a dummy variable. It's going to integrate itself out of the calculation. What's actually going to happen, you can note in our bounds, t null is going to be an observed value. That'll actually be a numerical value given to you in the problem. Whereas little t, the upper bound, is going to play the role of the independent variable in our description of r bar of t. It's going to be that independent parameter. All right? That's why u is needed as a dummy variable, because t is actually going to come back into the problem through the integration, and u is going to integrate itself out. All right? And a in this above formula is just replaced with t null, that observed or very specific unit in time where we observe a very specific unit in position. Right? Measurement in position, or description in position, I should say. All right? So, that is how we describe future value with those bits of information. And you might recall these as initial values problems looking at motion in space. These are problems that are similar to finding the velocity function given the acceleration function and some observed velocity, right? Back in Calc 2 in that motion in space problems, or you might relate this back to finding that position description, that position function, right? Given the velocity function and some observed description of position. This is more analogous to that position and velocity case. Because keep in mind, what does r bar at t describe? R bar at t describes position in space at time t. Position in our n-dimensional space in time t. What does r bar prime at t describe? It describes the rate of change in our position in space at parameter t. Now, I think I may have said time earlier, I mean parameter t. But if we make that parameter time, then here we have the case for motion, right? Which is our next scenario, or our next lecture is going to be on motion in n-dimensional space, where all of these connections are going to be made. All right? But let's calculate a future value with this. We look at a quick example here. We can wrap up this notes. Suppose r bar prime at t, the rate of change in our vector valued function here, is given by the vector 2t plus 1 comma 4t minus 1, this two-dimensional vector. And suppose we observe a very specific position, right, described by r bar of 0, right? Suppose we describe the position in our two-dimensional space at the parameter value t equal to 0. And suppose we observe that to be at the location 3 comma negative 3, right? Well, then the future value of r bar for values of t greater than or equal to 0 is going to be given by this. Our description of the vector valued function r bar of t that would be true for values of t that certainly are going to be bigger than or equal to our observed value, right, is going to be equivalent to this calculation seen here, where what we've done is gone into this above definition, and everywhere we've seen t null, right, replaced it with 0, because t null equals 0 in this setup. This is how we identify t null. It is that specific point in time where we observe a very specific location, right? So t null replaces, or 0 replaces t null here, 0 replaces t null here, and we notice that is just r bar of 0, this very specific location, and that's going to replace that value in our calculation seen here. And r bar of u looks a lot like r bar of t, except t is u. And that is true. That's what we've said above, is t is just going to be replaced with u, this dummy variable. So this t here is going to become u, and this t here is going to become u, and they're simply going to integrate themselves out in the process. Let's see that. If we set this up specifically, so r bar of t is just going to be that observed position, 3 comma negative 3, r bar is 0, observed right here, added to that integral from 0 to t. Notice 0 is taking the place of t null. T is the independent variable value in the parameter, or the independent parameter in our vector valued function r bar of t. All right? It's going to come back in as the variable description in this vector valued function, the independent parameter in this vector valued function. And all I've done is gone into my vector valued function, or the description of r bar prime of t, and replaced the t's with u's to act as a dummy variable, just as a variable placeholder, we sometimes say. All right? And I'm going to integrate this with respect to that variable placeholder, u, and allow t to come back in at the upper bound of this integration to act as the independent parameter in our description, our vector valued functions description of r bar t. All right? Now integrating this, they're both linear cases. The integral distributes itself across those cases. So the development of this antiderivative is not too tricky in terms of u. This is u squared plus u. This is 2u squared minus u. Its antiderivative seen below, which we're now going to integrate across these bounds from 0 to t. We start with the evaluation at t, which is just going to replace all of my u's in my antiderivative vector valued function with t, and we see that here in this result, and subtract from that what I would get if I replace all the u's with the lower bound of 0. Well, certainly the polynomial form results in the 0 vector, 0 comma 0 in two-dimensional space. If I now add up these three vectors, I will produce one vector result as my solution given by this polynomial. Well, this vector valued functions whose components take on this polynomial form, each their own respective polynomial forms. From the t squared plus 2 plus 3, we get t squared plus 2 plus 3. And from the t squared minus 2 plus negative 3, we get the t squared minus 2 minus 3 in value. And this here, folks, is our description of r bar of t. That describes our position in this two-dimensional space with respect to the parameter t greater than or equal to 0. We can use it now to describe our position at any location in this space as long as our value of t is bigger than that value of 0. Right? For any future value of time t. Right? That's where the future value idea comes into all this. Right? If we were talking time. Future value of the parameter, right, in general. And notice that is what we're finding. And we can find our description of r bar t in this context if we know its rate of change and we know just a little bit of information of an observed position at an observed unit of the parameter. All right? That all can be put together into what we call this future value calculation, which will actually yield a description of the vector valued function whose rate of change you have the description of. This, again, remember, is useful in conversion from acceleration to velocity and velocity to position back in calculus and just motion in linear space. But now we're going to move off to the description of motion in n-dimensional space, 2, 3, n-dimensional space, folks. Look at n-dimensional motion, and in that space we're going to be allowed to turn our wheels, our steering wheels, and drive in different directions or move in different directions other than just linear space. And we're going to want to be able to move from acceleration to velocity and velocity to position in those descriptions too. And that's where this future value calculation is going to come in handy. So that will all be observed in the next set of lecture here, where we're going to get into some motion in space. in our discussion. So stay tuned for all that. That should be out shortly. And I will stop there for the day, folks, and I'll go ahead and upload this video for you. So hope you're all hanging in there, and I'll see you next time.